This is the second lecture of Professor Nakajima. He's going to continue his lectures on moduli spaces of instantons and W-algebras.
Okay, thank you very much for coming. So I'd like to start with supplement to my lecture yesterday. So I consider space X with T action yesterday, and I mentioned that there's so-called equivalent cohomology group. We further assume X is a manifold, and the T action is a differentiable action. Then, like in yesterday, I consider the homomorphism associated with the inclusion, I star. So for simplicity, I only consider the case of homology group rather than cohomology group. Then I mentioned that after tensoring the fractional field of equivalent cohomology point, it becomes isomorphism. And then if we assume X to be manifold, then we can write down the inverse explicitly. I mean, it's already indicated in my examples, which I mentioned yesterday. Anyway, let me go on. So suppose XT fixed point set decompose into connected components like this. So X alpha is a connected component. And I restrict inclusion I to each connected component and denoted by I alpha. Then I can consider the homomorphism, pullback homomorphism associated with this inclusion. So it is a let me see. Maybe I should also say that this because this is I assume this to be manifold. This is isomorphic to each dimension X minus tau T. So this is so-called Poincare. So I hope you know what is in the Poincare for the usual manifold, and it remains to be true for equivalent cohomology and equivalent homology. Then I first go from homology group to cohomology group. Then I can pull back, and then again I apply. And it's also known that fixed point set is also manifold. So again, we have the Poincare. So we return back to the homology group, right after the pullback. So anyway, so I have a pullback homomorphism, and then I divide by the so-called equivalent Euler class of the normal band. Then this becomes inverse of the push-forward homomorphism. So n of x alpha x, this notation is a normal bundle to component x alpha in X. So if you consider that, so X is a manifold, so you can restrict to, you can consider the tangent space of X. Then you restrict it to X alpha. So it decomposes into the direct sum of the, or maybe it's not naturally the direction, but rather I should say that I have lost the pen. So the restriction of tangent bundle to X alpha contains the tangent bundle to a submanifold X alpha, as a submanifold, and then consider the quotient bundle. So this is isomorphic. This is by definition the normal bundle. And all T equivalent bundle over T equivalent bundle means action. Not only the space, you have an action on the fibers, and the action on the fibers are linear. So this is a definition of T equivalent. So normal bundle becomes T equivalent. Then you can consider the so-called equivalent Euler class. So I will not review the definition of equivalent Euler class, but I just to give an example. So suppose furthermore that this each x alpha x point component is a single point. Then normal bundle, I mean, because x alpha is a single point, normal bundle is just a vector space. So it's just a tangent, and also the tangent space to the component is just a trivial bundle. So tangent space at x alpha is nothing but the normal. And this is since x alpha is a point, so this is just a vector space with t action. So you can consider this as a representation of t. Then equivalent Euler class of this tangent space is product of weight. So you consider tx alpha x as a representation of t, and you consider weight as a polynomial on the real algebra of t. So recall that equivalent homology of a point is a polynomial function on the real algebra t. So since weight is a polynomial on the real algebra, so this product is as an element of the equivalent homology of the point. So this is a well-defined element. Then you invert that. So yesterday's examples, so maybe you remember, I hope you remember that. So I computed inverse of the push forward, pull back. Then you see this kind of expression in the denominator, right? For CP2, it was x2 minus x1. And for C, it was 1 over x. So this x, or x2 minus x1, is the equivalent Euler class of the tangent space at x. So I will not use this results in later of my lectures, but somehow in fact in many computations, I mean which I will not mention, and I just probably mention the statement. But in the proof, this kind of computation on the tangent space and its weights are used in the proof. This is some basic result in the equivalent homology. And also, if you know that the wire character formula of the finite dimension representation of complex simple group, maybe you notice that this kind of expression appears in the denominator. And there's some close relation between this wire character formula and this inverse of the localization. Okay, let me go on. So now I start to talk about the space which we use to construct vertex operator algebra. So this is the Instanton modular space. And as I said, so we take a very simple for manifold, so R4, and by technical reason, I consider it's 1 point compactification. So S4 is 1 point compactification R4. So then I first take compact Lie, which I denote by K. I assume this to be simple vector. And I consider the so-called framed modular space of K instantons on S4 with charge K. So you don't need to understand what the space it is. But somehow this is some space. At first, this is some space, topological space. In fact, KSI affine algebraic variety. Depending on two data. First, K is a positive integer, non-negative integer, sorry. And large K is a Lie group. I always fix the Lie group. So this is some space. And by some technical reason, this space doesn't behave well. So this is non-compact space, and we want to consider compact space, for example, T, in order to consider the integration. So in homology group, push forward is something to do with integration. So we do want to have integration. But in fact, people notice that it is more better to not to consider the compartition. Instead, better to consider the partial compartition. So which is denoted by U of KK. So U stands for Uhlenbeck. So this space was first introduced by Uhlenbeck. So theoretically, this is a disjoint union of Instanton modular space with smaller charge. So L is a charge which is smaller than or equal to K. And for difference is a symmetric product of the base space R4. So Sk minus L R4 denotes the symmetric product of space R4. So this is you first take Cartesian product. So this is K minus L. And then you divide by symmetric group. So this is an unordered configuration of points. K minus L unordered points in R. Okay. So this is some space, and UK in fact is known to be affine algebraic variety. So in that sense, this is a nice space which I briefly mentioned when I start to talk about equivalent cohomology and equivalent homology. And in fact, when K is SUR, so this type A B group, there's the so-called ADH description. So this is alternative description of this Instanton modular spaces. So instead, Instanton modular spaces, I as briefly mentioned in the first part of my beginning of my first lecture. So this is a modular space of solutions of certain partial differential equations. But ADHM description is much simpler equation. This is an equation on linear matrices, algebraic equation instead of partial differential equation. So this is a nonlinear equation, but algebraic equation. So in that sense, much easier to handle. And if you know something about quiver varieties, which I introduced many years ago. So this ADH description is ancestor of quiver variety. So if you want to know the details, please look at my book called Lecture with title Lectures on Hilbert schema points. And chapter 2 contains the discussion of this ADH. So anyway, so you don't even need to know what is the ADH description. So anyway, so you just please accept that this space have alternating useful description. And one of the application of this existence of this description is the following. So one can construct slight modification of UKK, Uhlenbeck space, which I denote by M or KR. So R is this rank plus one. So this SUR and this R. Oops, why this is cut? Yeah, anyway. Something is hidden. Anyways. Oops. I should not do that. Okay, so MKR is some slight modification of UKKR, and it is the so-called symplectic resolution of this Riemann expression for SUR. So, and for R equal 1, I mean, somehow SU1 is excluded, but you can formally consider MK R equal 1. And this is somehow the basic building block, which I hope you could understand some flavor of this instant model space. So when R equal 1, MK1 is the so-called Hilbert scheme of points on C2. So first of all, Uhlenbeck space as a partial compactification of instant modular space doesn't make sense. But if you look at this description of partial compactification, so if you interpret all this M0 LK to be trivial space, empty except L equals 0, then this space is just only this symmetric power part appears, part remains, right? So this is in some sense, I mean, of course, it is strange that we starting with trivial space and empty set and get something non-trivial as a partial compactification, but formally this is considered to be U of K of U1. SU1, I don't want to, it's a little strange to write SU1, so instead I write U1. But anyway, so this is just a notation. This is formally space for U1. Then, so this is K unordered points in R4 or K unordered points in C2. And the Hilbert scheme of K points in C2 is a slight refinement of this symmetric product. So namely, Hilbert scheme points is as I said, it is a set of ideals in polynomial ring in CXY, such that this quotient is K. It is. This is K dimension. Okay. So if you have K distinct points in C2, then you can consider ideal polynomial function which vanishes on those points. So then it satisfies this dimension condition. And if several points collide, then you can, if you just formally consider the ideal set which vanish ideal function which vanish those points, then this dimension of the quotient space is smaller because if some points collide, then you can remove that point. But somehow this ideal, even if some points collide, it makes sense, and this becomes some kind of generalized point. Okay. So I will describe the fixed torus action fixed point. So I hope this will become clear soon. So it is more important to understand the properties of those spaces. So MKR or UK of K or MK of R as an action of T is equal to T cross theta 2. So T is the maximal torus of G, which is complexification of this maximal. So here you have this is the same, but this is T to the R minus. And this sister 2 acts on the base. Preserving the infinity. So you identify alpha with C2. So you have the induced action on the base. And I don't explain how T acts on here, but this comes from the so-called framing, which I skip the explanation. Okay, so this is the first property. Second, so there's a morphism for MKR to E of K of CR. And you get the scheme of points from C2 to the symmetrical power of C2. So this is the so-called symplectic rhythm, but the important point is this is proper math, proper continuous math. So for the case of Hilbert scheme points, so once you have this kind of idea, by you can somehow count so I mean, this is quotient space is k-dimensional, but somehow you can define this quotient space by considering also localization of this polynomial. So then you can consider the support. You can introduce a notion of support of ideal, and this is a configuration of it. So maybe I should not go into this. So this is some. I mean, if I is just polynomial function vanishes at distinct point, distinct k points, then this is just this becomes isomorph at this opposite. Okay. And one property which somehow you don't need to understand is this space MKR does not exist. Okay. Different from SR. So I don't make precise what do I mean by non-existence, but in many senses, MKR is very nice space. And if you look for similar nice space for other groups, there's some obstruction for finding such example. So MKR is known to be not non-existent for other groups. So this makes the analysis of instant modular space difficult for groups other than SUR. So this is an unpleasant fact, but you must. This is a status, so you must accept. Okay, and then we apply the localization theorem. So it is important to understand the fixed point set. So I use this notation continuously. So this bold T is a product of T and this sister square. And the T is a maximal torus. Oops. So I first consider the fixed point with respect to maximal torus of K, or complexification of K. So this is SK over 4. Or maybe I should say that. So I have M of 0 of K minus L, but this 0 times. This is not. But if Instanton charge is 0, then this is just a point, single point. So I omit this point. Okay. And MKR of T is more interesting. So I don't explain what T was, but this is the decision to union of some space parameterized by R tuple of integers, non-negative integers. And for each KRs, I consider the Hilbert scheme of points. And I take the product. So I have R Hilbert scheme of points, and I take a product and this disunity. So somehow MKR, at least MKR of T can be considered as colored configuration of points on C2, but this configuration itself is not the genuine configuration point. So this is refined to be Hilbert scheme of points. But you have R colors, and so you have those. This kind of description. And I don't, maybe at some point I might use the genuine MKR, but the most important property which you should understand is this property. The T fixed point is a product of Hilbert scheme point. Okay. Now we consider the extra sister square action. So Hilbert scheme of C2, and then I take the action of sister. So this was the set of ideals. The quotient is K. And what the condition for this is fixed by the sister square. So that means that I descale X and Y by scalars T1 and T2. And this ideal must be preserved under this rescaling. So that means I is a monomial ideal. So monomial ideal means spanned by monomial. So monomial is eigenfunction for this sister square. And if I is spanned by monomial, then it is fixed. And the converse is also. Then you can draw Young diagram like this. So this box is 1, and this box is X, and this box is X square. Okay, I do one box. This is Y, and this is XY, and this is Y squared. So you surround monomials, which is not contained in the ideal I, then you get this Young diagram. Because once you have this X square Y is in the ideal, then all the monomial which is the right of the X square Y or upper of X square Y are also contained in the ideal. So then it means the remaining piece must form Young diagram. Okay. So in particular, so this is isomorphic set of partitions. Okay. So I denote the partition. No. So lambda is lambda 1, lambda 2, so on. I think I will not use my convention, but I think this lambda example is 3, 2, 1. So this is my convention. Okay. So combining two, this MKRT, this one, and Hilbert scheme points has correspond to partition. So if you consider X point of the large group action, so this is vector lambda, lambda 1, lambda 2, up to lambda r. So this is R tuple of Young diagram whose total size of the box is equal to K. So this is the description. Okay. And then I also need to use the so-called tautological bundle. So this is a tautological vector bundle over MKR. So this has no So if R equal 1, so Hilbert scheme points. So as I said, this is pi. So ideal such that this is K dimension. And over here, so this I is a point in Hilbert scheme points. Then you can consider vector space, very natural vector space. So X modulo I. So if I vary I, then this V changes. So you have a family of vector spaces. And in fact, this form a vector bundle over here. Okay. And this, by definition, so because Hilbert scheme of K points means that this quotient is K dimensional. So this vector bundle has rank equals K. Okay. And more generally, so V is a vector bundle of MKR. Rank is against K. And so it contains product of Hilbert K1 times. So I may just talk, anyways, I only consider the Hilbert scheme points on C2, so I may omit C2. So as a fixed point of the smaller torus action, we have this space. Then if I restrict V to here, then this is just isomorphic V for Hilbert. Direct sum of the tautological bundle for Hilbert scheme. And the sum of K1 to KR is equal to K. So in total, this vector bundle has rank K. Okay. But I only need I don't need the definition of the tautological bundle. So I need only the property of the vector. So I consider the equivalent Chern class. So this is ice equivalent Chern class. So I'm not sure you know what the Chern class is, but anyway, so this is, so if you have a vector bundle on some space, you can assign cohomology class of degree 2i on the base. But maybe I didn't mention that the action, torus action on MKR lifts. So this is T equivalent. The torus action of MKR lift to the action on V, and if you restrict to the fibers, this is linear action. And if you have such a vector bundle, then its Chern class is an element of equivalent homology, equivalent cohomology. And I's Chern, so for I stands for 0, 1. C0 is 1, but normally people introduce that, and it is up to rank of. Okay. So this is some element. And if lambda is a tuple of partitions, so this corresponds to fixed point, T fixed point, EMKR. So I denote I of lambda. So this is the inclusion. So I identify lambda with fixed point. So I consider this inclusion. Then I consider the pullback of this ice Chern class. So this is an element of equivalent homology of this fixed point. But this is just degree 2i part of polynomial function on the real algebra. And this is similar to the case of equivalent normal bundle, which I mentioned in the inverse of the localization theorem. So this is determined by weights. This is some product. This is a polynomial. This is a polynomial defined in terms of weights. In fact, this is I's elementary symmetric function. And the variable is weights of V restrict to this fixed point. So if you have T equivalent vector bundle, and if you restrict to fixed point, so this is a T module, T representation. So you can consider its weight. And this is rank R, rank is K, and you have K weights, and you consider the, so this is K. So you consider the asymmetric function from I equal 0 to K. So this is the definition of, well, not the definition, but this is a property of equivalent Chern class of equivalent vector bundle at fixed point. And V restricts to two weights, to tuple of partitions. So weights of V, maybe I don't use this very fine information, but somehow I just want to mention that. So once, maybe I start with describing instant modular space, some abstract space. But in fact, in practice, this is a very concrete space. You study the torus fixed point, and you compute various weights of the some T representation. which is naturally assigned to this space. So this is very much combinatorial object, which appears many times. I mean, which is very similar to flag varieties and such kind of space which appears in Université. So anyways, I just described this, from which you see some flavor or combinatorial flavor of this space. So I have two pools of partitions. Too small. Maybe a second. So I wrote additive notation. So this I assign 0 to here, and this is epsilon 1. And this is to epsilon 1. And this is epsilon 2. So I have this is lambda 1, this is lambda 2, this is lambda r. So for each box, I assign those weights. And I also, because I must remember that this is coming from the second partition. So I add a of 2. So this plus those functions, those linear functions. So I, instead of variables x1 to xk appearing in elementary symmetric function, used in the elementary symmetric function, I substitute those linear functions and then consider the elementary symmetric function. Okay. So maybe I just need to fix my convention. So as I said, this is C of the algebra of T, which is C of the algebra of T times system 2. And I denote epsilon 1, epsilon 2 for additive characters for this. And T is R minus 1 dimensional, but I consider A1 to up to AR standard coordinate, and I assume A1 plus that plus AR is equal to 0. Okay. So this is the description of weights of the tautological vector band at fixed points. So you have this kind of combinatorial expression. And if you compute the equivalent Euler class of the tangent space at fixed points, then you see the leg length and arm length, which appears in the combinatorics of Maclaurin polynomial. So you have this kind of combinatorial flavor for this modular space. Okay, so this is the end of the explanation of geometric properties of modular spaces. So any question? Okay. By the way, so I should mention that. So I asked to upload my note yesterday to website, so you can find it from somewhere in the website. Okay. Now I start to connect those space.
Sorry, I have a question.
Yeah. Okay.
So for r bigger than 1, I have not understood. MKR is a Kuiper variety or is a new object, different object?
This is a Kuiper variety. Example of Kuiper variety.
And just to make it for type A R minus 1.
This is the Kuiper is the Jordan Kuiper. I mean, of course, this space is considered before I introduce Kuiper variety. But if once you accept the definition of Kuiper variety, this is quiver variety associated with this Jordan quiver. And we put the framing. So this is CK and CR. And I consider linear maps like this. Any other question?
Thank you.
Okay, I start to get representations there. So I first construct Heisenberg algebra. So I just mentioned that the Hilbert, so I consider Hilbert scheme points. So under the say, I omit C2 because I only consider C2. And so maybe in this case, I did not S to C star square. And K of S is partition of K. So H star of S equivalent homology of Hilbert scheme points. And if you tensor this fractional field, then what I explained yesterday, so this is the equivalent homology of fixed point, which is partition. So this is rational function in epsilon and epsilon, right? I again take standard coordinate epsilon. And I take the direct sum of all partitions, K. So there's a value, I mean, of course, I hope most of you know that partition appears in many places in representation theory. So this has the size of Fock representation. Of Heisenberg. Okay, so this is bosonic Fock space and can be identified with symmetric functions in infinitely many values. So this is so far as an isomorphism of vector space, and I just computed the dimension. And this is, I mean, it corresponds to partition. So it doesn't say much, but in fact, you can say much more. So one can realize, one can construct. Heisenberg representation on non-localized one. Let me see, somebody say on the chat. Okay. So you consider the direct sum of equivalent homology of a point. Then you can construct the Heisenberg representation. So this construction is geometric. So you consider the following diagram. So I consider the Hilbert scheme K plus n points, and product is Hilbert scheme of K points, and also some extra piece, which is C2. Then I consider the following subset, which I denote by Pn. So I mentioned that Hilbert scheme points are ideal. So I consider I1, I2, and the point X. And then I impose the following condition. So I1 is ideal, whose codimension is K plus n in polynomial. And I2 is codimension K in polynomial. So I impose this incidence condition. So I1 is I1 is contained in I2. Then I can consider the quotient. And by considering localization, you can talk about the support. And this support is concentrated at single point X. So this is the condition. So if I1 and I2 are distinct K points and distinct K plus n points, then I1 is subset. I2 means that this K points is contained in K plus n points. But this quotient is a remaining n points. And I must consider that those distinct, the n points are not distinct. I mean, it's concentrated a single point. So that example is not contained in Pn. But somehow, in some sense, so maybe you start with K distinct points, and you choose a point X, and you somehow add some points, n points in general sense, like the case of Young diagram. And so I1 is functions on vanishing on such point in general sense. Okay. So this is in fact, this is not just subset. This is close to subvariety. In general, this is singular, so this makes it a little bit difficult to deal with, but many results is known for here. For example, dimensions and irreducible. So this is irreducible. And then you have projection P1 of K plus n, and P2 is K opposite. And it is known that these both map are proper. Maybe I should, did I say that important property? Maybe I hope this. Yeah, maybe I should say that these two spaces, those are smooth. I mentioned that this is symplectic resolution. This is smooth. I mean, this is manifold. So in particular, Poincare derivative. So I can switch from cohomology to homology by Poincare derivative. Okay, so this is crucial for the construct. So I'm going to move this. So since we can, we have the isomorphism of cohomology and homology group, So I can pull back. So I use P1 and P2. You can both pull back and push forward with respect to P1 or P2. So if I consider this as a cohomology group, you define pull back. But if you want to have push forward, then I using this Poincare duality to going to homology group and then push forward. So you must, because the degree is changed in this way, you must be a little careful about how the degree changed. But so you can chase what is the change. And from now, I don't want to keep track of the degree. So when I say that some map is a map between homology group or cohomology group, I may not be this. It may not preserve the degree. So degree is somehow might be shifted, but I will not mention that. So anyway, so I have P in C2. So this is a fixed point. So this is the origin. And I consider alpha in H star of S of P. Then I can consider the following construction. P1 star of P2 star of something cross R. So this is, which I denote by P minus N of alpha. So this is H star of S of K to H star of S of Kyoto plus N. Right? Maybe I go straight. I must make it. Okay. I use this diagram. So I take the homology class on here, and I take, sorry, this is close, not. So I omit the C2 for here, but this C2 is this C2, right? This C2. So I have a homology class here, and take a product with homology class in here, and then pull back, and then push back by P1. So this is the formula. And on each this equivalent homology, so you have H star S of P. As pairing defined by some sign convention. So this is just okay. By a cup product. And I denote P of N of beta is adjoint of P minus N of beta. So beta is another class. Yeah, this is essentially one dimension, so you have no choice, but for later purpose, I do not. I use a different. Then this is a map from in the opposite direction. H star of S of scheme of K plus N points and send to here H star of S scheme of K points. Okay. And this will be, this P minus L is creation vector. And this is annihilation. the theorem, which I proved in 94, maybe 96. I don't remember which year it is. Maybe 96. And independently shown by Broniewski. So these operators satisfying the Heisenberg relation. So you have this inner product. Alpha, inner product of alpha and beta on theta. Okay. So I will take alpha from now. I take alpha is the fundamental class of P, this fixed point, and beta also. But then what is this product alpha? So I think I consider the simpler case. So I consider C and I have C star action and the fixed point towards P. And in this case, I say that I star of P is X times C. So in that case, X was the equivalent variable, so maybe I should change to epsilon in our case. So this has weight epsilon. I mean this torus C star. Then this is epsilon times. So in our case, this alpha, or more precisely, I star of alpha, alpha is P, is equal to epsilon 1 times epsilon 2 of theta. So this becomes epsilon 1 times epsilon 2 because the tangent space is now two-dimensional. So in the previous case, tangent space is one-dimensional. And the equivalent Euler class is the product of the weights. So in the previous case, you have only one weight, so it's epsilon, but in this example, we have two weights, so this is product of epsilon 1, epsilon 2. And this C2 is a Poincare dual of 1. So when you take a product with 1, it is a unit. So this is beta. It's C2 of epsilon 1, epsilon 2. And the beta is still P. So P is a point. So if you integrate over C2, this becomes 1. So this is, you remain just epsilon 1. So this is the answer. So this Heisenberg algebra is in fact defined over polynomial ring in epsilon 1, epsilon 2, and the commutator relation. Here it becomes, this coefficient becomes epsilon 1 times. Okay. So you can normalize, so you can eliminate this epsilon 1, epsilon 2 by renormalization. A definition of Pn. Oh, sorry, maybe I switch again. No epsilon 1. So there are several ways. So one way is take alpha to be P, but beta, you take beta to be C. This is one possibility. Then you repeat this computation until you see that there is no epsilon. Or you can also consider more symmetric choice. So X is, so you have X and Y. So alpha to be Poincare fundamental class of X axis and beta to Y axis. Then product of sheets of alpha and beta is you just count the intersection of X-axis and Y-axis. In general, you must take the intersection carefully when, so you may have several intersections and you may have multiplicity. But in this case, this is transversal. Okay. So after suitable normalization, you get the usual Heisenberg algebra. Okay, the proof of this theorem is not, unfortunately, it's not illuminating at all. So I somehow managed to compute this, and I check this relation. And apparently, I don't have any reason why this such relation is true, but I just proved it. So again, when I mentioned in the beginning of my lecture, so this is some fact which I can prove by experiment, but I don't know. I have no how to say theoretical or philosophical explanation why such result is true. But this is an example of the result which was generated in various directions. But at least somehow I just want to explain some computation. So I consider the m equal 1 and n equal -1 case. So P1 and P minus. Commuted. It's 1. So I try to apply Young diagram. So Young diagram is a fixed point, and you have the corresponding fundamental class as an element of equivalent point. And then I apply this operator P1 and also P minus 1. And eventually I want to commit it. So important point is you observe the those boxes. So cross is addable part. Addable means you can put a box, new box, to make a change this Young diagram to another Young diagram. And you also have this is black. Oops. Okay, I hope you see my screen. So in general, so if you consider the Young diagram, you can consider addable parts and removable boxes. And like illustrated in this example, addable part is always one larger than removable box. So this is one combinatorial fact. Then P of -1. So I take this point class. So this add a box to get a new Young diagram. And P of 1, so this is an annihilation operator, so this remove a box. Again, the result must be negative. Then I consider the composite P minus 1 and P1. So this is remove and add. And P1, I apply to lambda. So this is first you add and then remove. The order is different. But if so you get some mu, and the size, because you add one box and you remove one box, so the total size of boxes, total number of boxes is the same. If lambda and mu are different, so starting from this case, so for example, first you add this cross, and then you remove that box like that. So you get a different. But then this order is somehow irrelevant. Order of remove what is irrelevant. So in particular, so there's bijection, natural bijection between P minus 1, P1 and P1, P minus 1. So if you compute the commutator, so this commutator vanish. Four. So I'm computing the matrix element for lambda and mu, and if lambda and mu are different, then this matrix element is vanishes. But if lambda is equal to mu, then you add one box and then remove the same box. That means that you return back to the same diagram. But then you compare the number of possibility for add the part and removal of boxes, and as I said, the difference is always 1. Always 1 case. Larger than big. So this contribute to the commutator, and this becomes 1 because you have one case difference. Okay. Let me see. Or I mean, I don't carefully compute the epsilon, the coefficient epsilon, epsilon 2, but somehow this is something hidden in geometric discussion. So I omitted that part. Okay. So this is very rough idea how the high-dimensional algebra representation is constructed. And also, because we know that the dimensions of the equivalent homology group. So at least if you tensor with the fractional field, you can show that this is Heisenberg algebra. And also more by more works. Oops. So this is, in fact, something. This is, so you apply P. This is spanned by P minus M1, P minus. So you must use alpha. It's alpha. Alpha is twins. Back vector. So this is a fundamental class of cube 0 of C2. So for if you consider 0 point in C2, so this is just an empty set. Or maybe as for ideal, this is the whole polynomial. So this is just a point. Point as a space. Okay, and this is a fundamental class. So this is equivalent to homology class, and you apply the Heisenberg algebra colored with this alpha is equal to C2. Then you apply those elements. So this is an integral. This is defined over. So so this kind of integral structure is important when you consider. I mean, this is identified with symmetric space of symmetric polynomials, and you can regard epsilon and epsilon 2 as a variable parameters for this symmetric polynomial. And in fact, this is related, closely related, this is related to Jack polynomial, famous symmetric polynomial contain one parameter. This parameter appearing in Jack polynomial is identified with equivalent variable with epsilon 1 of epsilon 2, minus of epsilon 1. Okay. So some people are interested in integral form of Jack polynomials, and that understanding such integral polynomial is relevant. This kind of statement is relevant to integral. Okay, maybe I don't have much time to discuss more general case. But maybe let me see. But I slowly want to start higher rank case. So again, I consider the case of SUR, and I use this MKR, and I consider this. Torus action. Then I mentioned that MKRT fixed point set is two problems. then at least, as in the case of the Hilbert scheme points, let us first consider the size, calculate the size of this equivalent cohomology by localization. Okay. So as I said, this is as basis by fundamental class of fixed point. And if I just to take direct sum of all case, then I don't have any condition on Young type. So this is R tuples of partitions. Then from this, you observe that this is, I mean, if you have one partition that was isomorphic to Fock space, so this is isomorphic to Fock space, tensor Fock space. So each partition contributes one Fock space. This is correspond to lambda 1, and this corresponds to lambda 2, and this corresponds to lambda r. So you have r copies, and just as a coefficient, this is you take fraction. Right. So this is the the size. This indicates the size of this equivalent homology. And you have the Heisenberg algebra for each. So PM1 of alpha, PM2 of alpha, and so on, up to PR. So this should be, or I mean, so at least, once you go to this description, right hand side, so this is a representation of R copies of Heisenberg. Or this is Heisenberg algebra for the torus, R dimension, the algebra of torus. T is T. So T is maximal torus of GLR. So I started with SUR and I compressified to go to SLR. But if you look at this picture, somehow you find that it is more natural to consider GLR instead of SLR. And that is one reason why I did not symmetric power of C2 as Uhlenbeck space for U1. So it's natural to replace SU1 to U1. Okay, so we should, so this construct, this Heisenberg algebra of T acts only after the localization. Localization means the tensor is fractional. So our interest is a genuine equivalent homology, which is defined over polynomial. So if you tensor this, if you invert something, then the Heisenberg algebra or the torus act. But this should not be the correct algebra acting on the genuine equivalent homology. So it should be some smaller algebra acting on this space. And in fact, it is the double algebra or GLR acting on this equivalent. So I will explain the construction tomorrow. This construction, the implementation. Okay, I stop now. Thank you for attention. Any question?
All right, are there any questions from the audience here?
Hi.
Hi.
I wanted to ask, is it possible, so you found the Heisenberg algebra as algebra generated by some correspondences that you explicitly wrote down, but sometimes in representation theory there's a slightly stronger statement that the algebra is the homology of a particular space. Is it possible to...
you mean the Borel-Bere theory? Or what?
Yeah, like Borel-Bere homology. You know, for example, if in some Hecke algebras or like in your construction of the Coulomb branch, there's like one space whose homology as a vector space is the underlying algebra. Is there analogous statement in this setting?
Well, I mean, you can formally consider the disjoint union of Hilbert scheme point. But I'm not sure this question is really well defined or not. I usually consider Hilbert scheme is a single space, although, I mean, strictly speaking, of course, this is the disjoint union of various dimensions. But somehow I feel that Hilbert scheme in total should be the correct disjoint union of Hilbert scheme is the correct space which you should consider. And my construction suggests to consider such kind of space.
But maybe it would be more like the self-fiber product of that kind of space. You know what I mean? Like.
Yeah, and also this disjoint union, I have a morphism to the limit of the symmetric product. So these pairs of the disjoint union of Hilbert scheme map to limit of symmetric power is the actual space which I am considering.
Okay, thank you. One more question. So you found the associative algebra as opposed to sort of, the vertex algebra in some maybe more explicit vertex algebra form. Is there like a conceptual reason that you can see why you actually get a vertex algebra from this type of construction as opposed to just some associative algebra?
Well, that will return back to the question which I asked in the beginning. And I did say that I don't have clear, satisfactory explanation as a mathematician. Experimentally, we find many examples. And physicists have some explanation because you start with 6 dimensions. But I hope maybe there should be some more mathematical rigorous explanation, at least why we should get vertex operator algebra. I mean, personally, I am not satisfied with current definitions of vertex operator algebra. That is, I mean, of course, you people start with conformal field theory, and I know the reason why people use this kind of discussion. But people found that vertex operator algebra appears in many other places. So maybe one should try to find better conceptual definition, like Berlitz Drinfeld. So they use, I don't remember what the terminal factorization or something. I hope there should be more how to say, different definition which is suitable for this kind of construction, which is a priori nothing to do with two-dimensional quantum fields. If we have such action, then maybe we could try to see such definition is useful to understand my construction. That is my hope, but I don't have any idea.
Could I just ask one more follow-up? So if you considered some different spaces instead of R4, like some other algebraic surfaces or four manifolds, is there a conceptual reason that you could, like in this case, you just identify the algebra and you say, oh, it's the algebra of modes of a vertex algebra. But if you picked some other algebraic surface, is there a way that you could
At least for the Hilbert scheme of points, it's almost the same. In fact, I did in this full generality. But the difference is instead of, so in this description, so I implicitly, for Hilbert scheme of points, this Heisenberg algebra is associated with one-dimensional lattice. But I just replace the cohomology, integer cohomology of, maybe not integer, so cohomology ring of the surface. Then I can consider the corresponding Heisenberg algebra, which is basically the copies of Heisenberg algebra. And if the surface has odd degree cohomology, then it is changed from Heisenberg to Clifford algebra. So this construction can be generalized to the surface. But for higher rank case, the situation is much more subtle. I mean, maybe you heard about the result of Donaldson. So Donaldson used the modular space of Instanton to detect very fine structure of fine difference of the four manifold, to detect the fine difference of four manifold using this Instanton modular space. I'm not sure that such kind of finer structure can be understood from representation theory. Well, maybe I hope the Gukov is considering such a question. So eventually we may have some good understanding, but I'm not so optimistic about in higher rank case. It seems if you just naively use modular space of sheets on surface, it doesn't behave well, and at least for defining Donaldson invariants, people do know how to deal with such modular spaces. But if you want to construct representation from homology group, then current technology cannot be used. That is my understanding. So it's, maybe I should say this is open question, which is really worthwhile to study, but I don't know.
What about this work of Negut?
Negut, I think he assumed that the canonical class to be positive. No, negative. I have in mind that the case of general type sums.
I see. Thank you.
Any more questions?
Hi. So in the usual AGT story, there's a sense in which there's a Riemann surface that you also pick. Did we make such a choice in this? Have we assumed something like that?
I don't catch the question. Could you repeat?
Right. So, okay. In the AGT story with the physics, you pick some four manifold, which is, I guess, what the question was before, but there's also a two manifold or a Riemann surface that's also chosen. Is there a sense in which we've chosen something particular here? It would be what...
In fact, I'm considering S1. I'm taking S1, and I consider corresponding Hilbert space. Maybe, do you see that my yesterday's note? Let me do it. Yeah, so I think this should... Yes, so I started with 6-dimensional theory, and for 6 manifold, you assign number, and for 5 manifold, you assign vector space. And I pick up a 4 manifold and consider x4 times sigma 2 and also x4 times s1. So I'm talking about vertex operator algebra, which is of course defined on vector space. So this is assigned for x4 times s1. I mean, of course, we can consider disjoint union of s1, but it's just tensor product, so nothing new vector space appears. But you could ask what kind of number you could compute from sigma. So that is various correlation functions appearing in vertex algebras. So this is, so people study that. So these correlation functions can be identified with some natural quantity which you want to compute in 4-dimensional gaze. That is more, I'm just talking about the superficial level of AGT. AGT, first, you should first identify the vertex operator algebra with homology or cohomology of the Instanton modular space. But then as a next step, you want to compute various integral over the modular space, Instanton modular space, and identify it with some kind of quantity which you compute in vertex operator algebra side. So people has been studying such problem in many examples and many computations known. But so far I don't touch this question. I'm trying to go into different direction. So I'm considering the case when what happens if I change the group from the unitary group SUR to other more general group. And that is what I'd like to talk about tomorrow.
Right. I see. Thank you.
Any more questions? Perhaps from the Zoom audience? So I have a question that is related to the previous questions. So if you if you view you mentioned factorization algebras. So in Beilinson and Drinfeld's, this Heisenberg algebra, the vertex algebra structure appears in the factorization world related to the factorization of line bundles. So it's dominated as a space, is the space of line bundles on a surface, but trivialized away from a bunch of points. So I wonder if this action appears geometrically as an action of pick of the Picard of a Riemann surface acting on the Hilbert spaces.
Yeah, so the one of the problem which I could say in this construction is that, so I say that I assign vector space to S1, and as I said, I expect some number of function assigned for Riemann surface, but somehow I don't see at all what is S1 and what is sigma in four-dimensional gauge surface. I mean, of course, I say that this should be understood as a cohomology. This assignment should be regarded as cohomology of the Instanton modular space. But why this Instanton modular space is something to do with S1, that I don't see. And in particular, I think that at least factorization, I don't remember the axiom of the factorization algebra, but somehow they started with curve, algebra curve, but I don't see this algebra curve at all. So maybe this is maybe this is the reason why I don't see the actual philosophical reason why this construction works. But somehow, yeah, I don't see any reason why this cohomology group is something to do with this Riemann surface or algebra curve.
Okay, thank you.
Yeah, please consider such question. I mean, I think this is worthwhile to consider.
All right, so if there are no more questions, let's thank the speaker again.
Thank you for attention.
And we'll continue tomorrow. Thank you very much, Hirako.
Yeah, you're welcome.